What if dark matter isn't a mysterious exotic substance, but a subtle consequence of the difference between gravitational and inertial mass? Today, we explore an unexpected perspective. By revising Einstein's energy relationships, Osiak relativity halves rest energy, enabling negative temporal momentum without negative energy. This innovation reinterprets particle dynamics fundamentally. Harari and Shoup's Prion model reveals that quarks, leptons, and bosons are composite, reflecting near-equal matter and antimatter. This balance influences mass differences in surprising ways. Combining modified gravitational constants and distinct inertial measurements, the model predicts a dark-to-visible matter ratio near 6, derived from intricate Prion count and energy dynamics. Experimental approaches range from re-examining gravitational constant measurements to designing new tests. Variation with material composition could confirm this innovative model's predictions. In conclusion, rethinking dark matter through alternative relativity and Prion models challenges convention. Further experiments may revolutionize our understanding of cosmic mass.
The paper we're diving into today is Dark Matter as the Difference of Inertial and Gravitational Mass by David Lush.
Yeah, and wow, what a title, right? Dark matter as the difference of inertial and gravitational mass. It already hints this isn't your usual let's find a weird new particle approach.
Right. So the core problem Lush is addressing is the whole dark matter mystery. You know, galaxies spin way too fast to be held together by just the visible stuff. Stars, gas, dust. For decades we've wondered, what's this invisible, dark matter giving them their extra gravitational glue?
But here, Lush comes at it from a totally different angle. Instead of inventing new matter, he's basically saying, well, maybe the laws we use to add up mass, inertial versus gravitational mass, need a rethink. That's pretty wild, because, in physics class, weren't we taught those two are always equal?
Exactly, and that's key. So he's questioning something fundamental. Lush builds his argument by combining two unconventional theories. One is Osiak's tweak on special relativity, and the other is the Harari-Shoup model, which says that even the building blocks of matter, quarks and leptons, are made of even tinier things called prions.
Yeah, that prion thing is wild. In the Harari-Shoup model, every elementary particle is basically a combo of just a few types of prions and antiprions. So, at that level, matter and antimatter are thoroughly mixed together, which is not what we usually think.
Right. So, if you take that and then bring in Osiak's alternative relativity, which, among other things, apparently allows different ways of adding up energy and mass for composite systems, suddenly you can get situations where a lump of matter's gravitational mass, the amount it pulls gravitationally, is different from its inertial mass, the amount it resists being pushed.
Okay, so you're saying that in this hybrid theory, a hunk of matter might weigh more gravitationally than it weighs when you shake it or put it on a scale?
Exactly. And that might sound bizarre, but Lush argues that we only measure mass via inertia, or the weight in the local gravitational field. But if these quantities diverge because of this prion-antiprion mix, we could be underestimating the true gravitational mass of, say, a whole galaxy.
So under this model, when astronomers measure the mass of galaxies using stars' orbits, the numbers seem too low. But that's because they've been using the wrong version of mass all along?
That's the idea. If we've been equating inertial and gravitational mass, but in reality gravitational mass is higher, then the so-called missing mass, the dark matter, is just this difference. It's not made of exotic new particles, it's baked into the fabric of what we already have.
One thing that fascinated me was that Lush even tries to estimate the ratio of dark to visible matter by tallying up prions and antiprions in a typical atom, like deuterium, and he ends up getting numbers that aren't far off the dark to visible matter ratios we see in observations, like 6:1.
It's definitely a hand-wavy calculation. He even admits that. but the fact that it lands in the same ballpark is, at the very least, pretty suggestive. But of course, these models aren't mainstream.
No, but it kind of gives you a different feel for what academic research means, right? Like, it's not that he's claiming absolute truth, it's more, here's a framework. Here's a way to see familiar problems from a new angle. And if it sparks an experiment or a new analysis, then awesome.
True, and he does mention possible ways to test it. Like, if you could somehow make highly precise gravitational constant measurements with test masses of radically different composition, you might see tiny differences. That would give a clue.
That reminds me of, I don't know, sort of like the early days of atomic models, when you know you're missing something, but you're not sure where the fudge factor is yet.
Or like, when people first suggested the neutrino to explain missing energy in beta decay. At the time, maybe it seemed desperate. Now it's basic knowledge.
You know, I think I read somewhere that most dark matter searches have been looking for new particles, and, well, nothing so far. This paper offers a reality check. Maybe we're barking up the wrong tree?
Or at least, maybe we shouldn't rule out wild alternatives. The paper we're diving into today is Dirac Quantum Theory Using Alternative Relativity by David Lush. It's quite a dense read, but wow, there's a lot in there to unpack.
Yeah, I have to admit, when I first saw that title, I thought, here we go. Someone's ruffling the feathers of physics again. But, you know, it's actually addressing something pretty fundamental. How we reconcile quantum theory, especially the Dirac equation for electrons, with an alternative form of relativity, not the one we're all used to from Einstein.
Yeah, exactly. The core question Lush is digging into is, what does it mean for quantum theory, particularly Dirac's framework, if we adopt Osiak's alternative relativity, rather than sticking to textbook Einsteinian special relativity?
And right there, that's a big deal, because Einstein's relativity underpins so much of both classical and quantum physics. But Osiak's version gets kinetic energy from integrating the Minkowski equation of motion, so a fundamentally four-dimensional Lorentz invariant equation, instead of the usual Planck force equation that's only three-dimensional. That sounds subtle, but it totally shifts how energy is calculated.
The headline is that, according to Osiak relativity, the energy of a free particle is halved. Like, for a resting particle, its famous E equals mc squared energy becomes just mc squared over tav. Lush shows this doesn't break Dirac's theory for a free electron. In fact, it sheds new light on things like antimatter and the way matter and antimatter pairs get created and annihilated.
I liked that discussion about negative energy states in Dirac's theory, too. Traditionally, those negative energies get interpreted as antiparticles, like positrons, traveling backward in time. That's wild enough, but in Osiak's setup, those states have positive energy, but the temporal part of their form momentum is negative instead.
That's such a twist, right? We usually equate the temporal part of form momentum with energy. Osiak says, no, they're separate. The temporal form momentum stays the same as in Einstein's version, so the rules for things like particle creation thresholds still work. But what we actually call energy just isn't the same thing anymore.
And, honestly, that brings up sticky questions for conservation laws, which we've always considered almost sacred. In Osiak relativity, energy can be non-conserved, especially in highly relativistic collisions. But form momentum is still always conserved. It might sound like theoretical hair-splitting, but Lush argues that this could actually help explain puzzling phenomena like dark energy or even cosmic inflation.
It sort of flips the script. People worry about energy non-conservation, but maybe, in some extreme conditions, that's the missing ingredient we need. There's even a proposal that the so-called missing energy fuels universal expansion.
And there's this bit about photon energy, which sort of, tripped me up for a second. In Osiak's setup, a photon's energy is h nu over 2 instead of h nu. And that fits better with some old arguments about the standing waves in the blackbody radiation problem.
The way he links that to de Broglie waves is clever too. If you have the rest energy but use the electron's spin, Since electrons have half the spin of a photon, you end up preserving relationships between frequency, energy, and momentum. It keeps the mathematics of Dirac's theory intact, but the interpretation is well, you have to change your mindset about what's real.
And if you're listening, you might be asking, does any of this matter, or is it just mathematical games? Lush argues there could be experimental tests, like in pair creation events. He claims that if you could watch carefully enough, Osiak's relativity predicts the positron, the antimatter electron, should be detectable before the pair event, annihilating before it's even created. It almost feels like a physics prank, but that's what his equations say.
Right, so in principle, the difference between Osiak's and Einstein's relativity could be tested, at least if our particle detectors get fast and precise enough. Sometimes I wonder if, in 100 years, people will look back and see debates like this as the real groundwork for how we explain dark matter and dark energy.
I doubt I'll be around to see it, but yeah, maybe. Of course, the idea that all these conservation laws, like energy, are only true under some definitions is a little unsettling. Reminds me of when we learned that, Pluto wasn't a planet anymore. The definitions change, but the physics, well, the phenomena, are still there regardless.
That's such a great analogy. Science keeps evolving, and sometimes what we take as foundational is just the best story for now. The paper we're diving into today is On Einstein-Minkowski-Osiak Relativity by David Lush.
Okay, that's quite a title, right? I feel like just saying it out loud almost makes me smarter. But yeah, so this paper by David Lush is basically revisiting, well, challenging actually, some of the key ideas we all thought were settled in relativity.
The core question is, honestly, a wild one. What if the textbook version of Einstein's relativity isn't the only game in town? Lush explores an alternative called Osiak relativity that's based on different mathematical assumptions. Specifically, it argues that if you base your descriptions of particle mechanics on fully Lorentz-invariant Minkowski equations, so four-dimensional equations, rather than the usual three-dimensional Planck ones, you actually get different formulas for energy.
And it's not just some subtle difference. It literally changes what the rest energy, kinetic energy, and total energy of a particle are supposed to be. Apparently, in this Osiak version, the rest energy is E0 equals mc squared by 2, instead of the classic E0 equals mc squared.
Yeah, which, if you love your Einstein posters and mugs, kind of hurts, right? I mean, E equals mc squared is like the most famous equation in physics.
I know, but the significant thing here is Osiak relativity doesn't conserve energy in relativistic collisions the way Einstein's version does. Instead, it preserves something called the temporal component of four momentum. So, for all practical purposes, like the energy thresholds that smash particles together, they still come out right, but the underlying principle isn't energy conservation, it's temporal momentum conservation.
That is a lot to wrap your head around. I love that nerdy distinction, though. It's a reminder that the universe doesn't care about what's in our textbooks. But back up. Does this mean all the observed conservation laws are just aspects of momentum conservation in this framework?
Pretty much, yeah. If Osiak relativity accurately describes nature, then what we've been observing and calling energy conservation is actually a reflection of four momentum conservation. Which, honestly, makes me a little dizzy, but...
No, same. Because that's like saying all of these collision experiments we've done, all of physics built on those, maybe our explanation's been wrong, even if our calculations lined up. It's very, you've been using the right recipe, but you don't understand why it works.
Exactly. And Lush really stresses that this isn't just theory for theory's sake. Like, he mentions possible consequences for dark energy and dark matter. That if energy isn't strictly conserved, maybe that missing energy we attribute to dark energy or dark matter is just, the universe not keeping the kind of books we expected.
I mean, it would be kind of poetic if dark energy was just the universe bungling its accounting.
Or being way more clever than our equations. Oh, also, this is a fun side note, and then I promise we'll get back on track. Lush goes off about how, under Osiak relativity, the electromagnetic field should be complex valued, not just real, which could maybe connect to why quantum mechanics uses complex numbers everywhere.
Yeah, that's wild. Like, maybe the math weirdness in quantum stuff isn't just quantum is spooky. Maybe it's just our relativity being incomplete.
And to make it even more spicy, Osiak relativity resolves some persistent puzzles, like the spin-orbit coupling anomaly in atomic physics. In this new framework, the energy levels just make sense without introducing things like Thomas precession, which always felt kind of like a fudge to me.
This brings up a meta point, actually. One thing I keep coming back to, reading through this paper, is how scientific theories aren't absolute truths. They're frameworks. And sometimes we find out the framework we've been using is kind of off. But if it still made good predictions, should we care? Or should we push for something more fundamental, whatever that means?
Yeah. Like, does it matter if it's momentum or energy being conserved, as long as a collider produces the right amount of stuff? Maybe it only matters when we want to explain something that doesn't fit, like dark energy.
And honestly, listeners, that's the kind of philosophical rabbit hole academic research leads us down. Lush isn't claiming he's found the truth, but he's showing that there's more to explore. And sometimes that means turning long-cherished ideas on their heads.
If anything, it's a good reminder not to take textbook physics as unchanging gospel. The real universe might still have surprises up its sleeve, just waiting for someone to reconsider what everyone else took for granted.
Absolutely.
Welcome to In Depth with Academia. I'm Richard Price, CEO of academia.edu, and today, wow, do we have a fascinating and thought-provoking paper to discuss. We're diving into dark matter as the difference of inertial and gravitational mass. Yeah, you heard that right. The title might sound a bit dense, but trust me, this idea could change how you look at the universe. First, as always, I'm here to present this work neutrally. I'm not endorsing or debating, just sharing the author's perspective so you can ponder it yourself. Academic research is always evolving. Nothing is set in stone, right? This is our chance to explore and reflect. So let's start with the basics. The author is David Lush. His paper tackles one of the biggest mysteries in modern physics. What is dark matter? For decades, astronomers have realized galaxies rotate way too fast if we only count the stars and gas we can actually see. There's got to be more mass out there, something invisible, hence dark matter. But here's the problem. After years of searching, physicists haven't actually detected any candidate dark matter particles. No definitive sign of these mysterious things. So what if we're looking at this all wrong? What if we don't need exotic new particles? David Lush's paper suggests an alternative. The core question, what if the gravitational mass of ordinary matter is actually bigger than its so-called inertial mass? And crucially, what if this difference is enough to account for all those galactic oddities? That's a wild idea, but let's break down what it means. Okay, pause for a second. Let's digress. You know, this reminds me of when I first tried to assemble my own IKEA bookshelf and realized halfway through that maybe I misunderstood the instructions. Sometimes maybe the answer isn't to look for a missing piece under the sofa, but to look at the instructions from a new angle. Anyway, back to dark matter. So the paper draws on two not so mainstream ideas from theoretical physics. First, there's a proposed revision of special relativity by Osiak. It says basically that Einstein's equations for energy might not capture the whole picture. And the second idea, it's called the Harari-Shupe model, which proposes our quarks and leptons aren't truly fundamental, but made out of even smaller parts, preons. These are elementary particles, and they're antiparticles. Mix these two ideas, and you get something pretty unique. Here's the argument. If ordinary matter, what we, see every day, is actually a mix of matter and antimatter bound up tightly together, then its inertial mass, the property that resists acceleration, can be less than its gravitational mass, the thing that creates gravity. That's pretty wild. Okay, let's get concrete. Lush calculates for certain atoms like deuterium, basically heavy hydrogen, that the gravitational mass could be 7 times the inertial mass. Imagine you pick up a block of deuterium and weigh it or push on it. It behaves like it has mass x, but its gravitational pull on other objects, that could be 7 times greater. Suddenly, you don't need hidden dark matter. If every star and bit of gas is weighing more gravitationally than we expect, the observed galaxy rotations make sense. Now, method-wise, Lush takes the preon model and looks at the numbers, literally counting up preons and antipreons in atoms, asking how that composition leads to different mass behaviors under these new ideas. He checks how much extra gravitational pull arises from all this. The paper even refines the model, considers effects like quark-binding gluons, and explores if those account for any dark matter shortfall. Key finding, it's plausible, at least within this framework, that the dark to visible matter ratio matches observations, even if, the explanation is completely different from what mainstream physics assumes. So what does this mean for you, the listener? Well, if you're interested in science, it shows how radically new perspectives, sometimes controversial, sometimes even outlandish, can shake up old questions. It's a reminder that science is a process, a conversation, and that the search for truth is always open-ended. This paper isn't claiming to settle the dark matter debate, and I'm not claiming it does either, but it's a real example of academia's creativity. Let's wrap up. We talked about galactic rotation, alternative relativity, tiny building blocks called preons, and how the way we measure mass could be key to solving cosmic puzzles. No matter the outcome, the heart of research is opening our minds to the possible, trying out new ideas, and challenging what we